Right. Yeah, thank you very much. Yeah, welcome to this presentation. In fact, thank you for the opportunity that we, as part of the AUTOSAR Working Group Safety, we can present a bit about adaptive AUTOSAR in context of a more safe programming language, Rust here. Yeah, I would be talking about working group safety in general a bit, and then a quick overview or quick highlights of adaptive AUTOSAR before I would hand it over to our colleague and the subgroup speaker for Rust in safety, Christof, who would then, proceed further into more details regarding Rust and how it compares with C++. Yeah, on the agenda, you could see we would have then, a quick structuring of working group safety, the different subgroups we have there, and then the characteristics of adaptive AUTOSAR, then methodology, and proxy and skeleton generation. So that would be my part. And afterwards, Christof would take over for the Rust for AUTOSAR applications, the game changers of Rust, and outlook and further reads. So yeah, this is what our four subgroups within the working group safety in AUTOSAR looks like. The first one on the left-hand side, as you see, is called Platform Health Management. There is in ISO 26262 part 6, a paragraph which talks about external monitoring, hardware controlling, and so on. And that is our solution in adaptive AUTOSAR, where we perform different kind of supervisions on supervised entities. These supervised entities normally would be processes. And the kind of supervisions that we do are, for example, a live supervision where we check whether the supervised entity is stuck or is it still working. And then you might have deadlines for performing specific tasks that could be supervised as well. Moreover, also a control flow logic could be considered or could be supervised. If there is any deviation, then we know there's something that needs to be done about it. Health channels is also another interesting supervision, which is doing it more from a hardware perspective for things such as voltage or temperature, and that could be supervised. So that's one of our subgroups. The other subgroup that we have is called end-to-end protection. So again, in the ISO 26262 part 6, appendix D, there are about 10 faults, communication faults that are mentioned for the embedded systems. And our response to that from AUTOSAR is then this end-to-end protection mechanism, which is basically we have different profiles. These different profiles are a combination of the parameters that you see here, majorly a combination of length, counter, data ID, and CRC. And the last three that have been mentioned here, they are more relevant to methods, some IP methods, so message type, message result, and source ID. So a combination of these parameters make a profile, and these profiles could be integrated by the OEMs in their projects. So that's the second working group, the subgroup. The third subgroup within working group safety is functional safety architecture, which produces a document called RS Safety, so requirement specification for safety, which intends to be the single source of or the single most important document that a functional safety engineer can use in the AUTOSAR domain, and really see how adaptive AUTOSAR could be made safe. So we have there some recommendations. Currently, it's on adaptive AUTOSAR. It would hopefully be also enhanced to then classic AUTOSAR, though there are for classic AUTOSAR also some existing things, mechanisms. Moreover, we working group safety are one of the 4 lead working groups in the AUTOSAR consortium. What does that mean? That means that anything that comes in the AUTOSAR specification has to go through our eyes. And there are 2 possible ways how things can come into the AUTOSAR specification. One is through changes. So one or two of our members, representatives, sit in the change control board who take a look at every change, whether it seems fine from a safety perspective. Similarly, the other way how things can come up in AUTOSAR specifications is a broader subject, a broader topic, which needs to come in as a concept. And also for this concept, there are lead working groups who should at least see this through, whether the concept does not have any impact with respect to their own domain, which in our case would be safety. So this is the role of the functional safety architecture subgroup. Last but not least, in fact, the highlight, what we would like to discuss more today is the Rust subgroup. This has been formed this year, and the idea is that we give indications on how adaptive applications can be developed in Rust, which is from a safety perspective, a quite safer language. And how to do that. For that, we plan to give an explanatory document as well as then a reference implementation on our prototype code that we call Adaptive Platform Demonstrator. In the future, hopefully, we'll also talk about then implementing software components in classic AUTOSAR in Rust, but that's something for the future. So I would just briefly like to tell you about the characteristics, high-level characteristics of adaptive AUTOSAR. So when this whole idea of adaptive AUTOSAR was generated in 2017, we thought one good thing would be to make reuse of standardization and avoid reinventing the wheel. So we have collaborations with other communities and can learn from them. Then one of the key features we thought was, okay, safety and security is something that cannot be compromised, especially in the automotive domain, especially now if we're going more towards over-the-air updates and autonomous driving. These have higher pressures on safety and security. The decision in the beginning, or what still holds true, is that C++ would be the language which the development language for adaptive AUTOSAR, and that still remains true. Then comes one other characteristic, that is the service-oriented architecture, which means that this is more of a scalable architecture. And we could have like server clients architecture enhancing our applications, consumers, and so on. Then, of course, one of the habitat where now these adaptive AUTOSAR projects will be used are in those very high performance ECUs, which also means that you need to leverage it from your programming perspective, and parallel processing is then one of the key features that needs to be considered or kept in mind while we are doing the standardization. Then plant dynamics, this is, let me say, our own word. This might be used in different contexts by different places, but what we really mean in adaptive AUTOSAR is that we can have in runtime changes and updates to the applications, and they could as well as modeling, and they could be adopted in runtime. Last but not least, one of the decided factor or the decided characteristic of adaptive AUTOSAR was that we would be using a POSIX-based system. And this is how we then had some collaborations with the automotive working group here at ELISA, and thought of these kind of presentations here. Moving on, I would just quickly say a few words about the methodology, the development methodology of AUTOSAR, and how we use that to have proxy skeleton architecture pattern then basically generated. So I would quickly like to show you this figure where you see that we have, we firstly define some services, and these services are then configured in some tool. for service interface description, typically an ARXML. At the same time, what you see below that is that we have then also machine manifest or configurations that would be relevant to the machine or the hardware itself that that the adaptive AUTOSAR is intended to work on. And from here on, we see that from the service interface description, after that, the developers start developing the adaptive applications, but have to consider whatever services they want can be grabbed with a bit of an easier workflow, that these then generate proxies and skeletons, the header files, so that the whole development doesn't have to be done from the scratch, but from the configuration, it could just be grabbed. Yeah, and typically once you have your integrated software and defined and configured service instances, they are then formed into a package or packed into a package, which would then be distributed or would be deployed on the actual hardware or the actual system. And that would contain something like an executable. Execution manifest is basically a configuration complementing your code, when to start, what to start, and so on. And then also service instance manifest. All this is then, of course, then deployed onto the hardware. So this thing, I think we can skip for now, but the idea was that I could give you a first insight on what the methodology looks like. Going a bit further with the concrete thing that we have here is then what I mentioned in the previous slide. We have a service interface definition. And from this configuration, we would like to give this, pour this configurations into a generator, which would generate headers for us, proxy on the consumer side, skeleton on the service side. And so that you could write the applications, just use these header files, and then you have the connection between these applications and the middleware transport layer. So yeah, that's probably it, what would set the basis for then the further discussion that my colleague here, Christof, would take over then.
Thanks a lot, Huzaifa. So I would like to introduce you to the results of, or some of the results of the Rust working group at AUTOSAR. So basically, we just, if you go to proceed to the next slide, Huzaifa, please. We would like to produce a demonstrator which uses the Rust programming language, which is a safer, more modern language, which was designed at Mozilla to actually make browser development less difficult and error-prone. And we believe that this is a perfect fit for safety or security applications. And but there is a catch, of course. Adaptive AUTOSAR is fully specified in C++, and it's also programmed in C++. And it compiles with CMake and G++, typically within a Yocto environment. And Rust typically uses the cargo build environment and an LLVM-based compiler. So C++ code compiled by one of these compilers will not be compatible with the other one. So we had a challenge at hand. And we solved this for now by creating two binaries. One is a shared library, the other one an executable. And these two interact with each other over a C interface. In addition, the C++-based adaptive AUTOSAR environment uses multi-threading a lot and uses standard promise and standard future. So C++ 11 features for this. And we decided for Rust to use a much more modern environment to use threading. And this is basically the async environment, which I will present a bit more later. Or C++, lifetimes of objects are typically, at best documented. You have to make sure that whenever you pass an object to a subfunction, that it's clear whether the ownership will be passed to that subfunction, and the subfunction has to free that that object or deallocate that object or not. And with Rust, this is documented within the language. And this, of course, means that especially bounds to lifetimes on objects should be visible from the source code. And this is not obvious from looking at C++ code. I will just show that within the next slide with some example code. And another key difference between Rust and C++ is that C++ or C uses a lot of shared mutable state. And it's typically checked by the programmer on whether the access pattern is correct and all the mutexes are properly held when you access data. And for Rust, the compiler will do this, and this helps a lot, but it also makes using a mutable shared state a lot more difficult. If you just proceed to the next slide, please. So there's a lot of text on this slide. I would just like to point out a few key points here. The second line is the introduction of an environment, which is env. And this is totally missing from the C++ side. This env is an AUTOSAR environment, and it's created by the initialize function. This is the first function being called on the C++ side. And it's destroyed by the deinitialize function, which is the last one, called within main. And all the other objects cannot outlive this bracket of environment. And this is not visible from the C++ side because, of course, you can still use a logger after deinitialize from the C++ side, but it might not work because part of the objects it references might no longer be valid. On the Rust side, we just use this bracket using this closure, and this will take care of this explicit lifetime. There is still some more classic function calls, for example, the end-to-end transformer function initialization, the configuration of that one, which is in the middle of the code. And this one still uses public shared state to do this. And we would like to just handle this. Right now, it's more influenced by the C++ side of doing things. And you can also see the question mark within the fourth line. This question mark is Rust's way of handling exceptions. This is basically a throw and catch. So whenever the environment set default function returns an error, this error will be forwarded to the error core async main function, which will then forward it to the main function, which will then exit printing the error and with a non-zero exit value. So this result propagation, this question mark operator, is a very nice feature of Rust because it just makes error handling more explicit. It also enforces error handling because you don't have access to the underlying value unless you explicitly handle these errors. So if you just proceed to the next slide. So now I would like to talk a bit more about Rust in safety. So with Rust in safety and the argumentation, actually something called soundness is very interesting because soundness is basically a property of a code base, which means that the compiler is able to verify absence of undefined behavior. Think of it as something like the compiler actually making sure that your safety manual is taken care of. And also API variants are not violated. So once we assume that the code is sound, we can actually rely on the compiler's guarantee for freedom of interference, which applies both to making sure that buffer overflows will not happen, also that shared mutable state is properly handled and guarded by mutexes, and that no additional thread local objects are being forwarded to other threads by using the send and sync requirements by the Rust compiler. And this brings us back to soundness. The Rust compiler will take care of ensuring the soundness of the whole system as long as all its subsystems are sound, which makes it more easy to just determine the safety of the whole system by just looking at subsystems. And the Rust compiler will take care of the rest. Also, Rust makes a lot of things explicit, lifetimes, cloning. There's no implicit casting with Rust. And Rust is very fashionable with security researchers. And it has seen a lot of variety of verification tooling cropping up during this year. Canny and Prusty are the most prominent ones, and Mir and Loom have found many problems in unsafe code. So there's an escape hatch for all the safety guarantees the compiler does, which is called unsafe. And this clearly marks code which will not be checked by the compiler, but has to be verified by human intervention. And we have formed a group at SAE International. And this one is collecting ISO 262 recommendations for Rust. Can you please proceed to the next one? The Rust compiler, since roughly 4 years ago, comes with a very interesting new feature, which only very recently made it into C++20. And this is coroutines. And this is basically a compiler-generated state machine or a function which is just resumable. This is a game changer on bare metal, and it provides really highly efficient and portable multitasking features. And it pairs very well with IO-Uring, which is the current highly seeing a lot of development on Unix as well, or Linux as well. This makes the code more readable, but lifetime reasoning is more complex because any references you pass to a function might outlive the calling of that function because there's additional state which is collected within that function and then handled by the executor. And also mixing async and non-async code is very difficult. Also, both Rust and C++ are still evolving here. If you proceed to the next and next. So within the AUTOSAR working group so within the Rust working group within AUTOSAR, we already showed that adaptive applications are possible within Rust. And we would like to have the code generation finished for the next release, which will be in November of this year. For next year, we planned to address classic AUTOSAR, which I personally believe a lot will benefit from the async environment, because this is a game changer for bare bone and especially no operating system environments. And there's often a talk about rewriting the AUTOSAR stack within Rust, but there might be a middle ground, which is just using existing SumIP or DDS libraries and combining them with some generated code. And you get a system which is very similar to an AUTOSAR stack, but just is full Rust, fully async, and yeah, can interface with applications written in C++ as well. If you just proceed to the next one, the first link just gets you to the AUTOSAR organizational webpage, and this gives you access to all the published standards. Unfortunately, the demonstrator code is not there available there unless you are a member of the organization. If you are interested in Rust for functional safety, the compiler, the company doing the compiler qualification will be interesting. This is Federal Systems in Berlin. I already mentioned the task force at SAE International. And within the task force, there's one person which collects a tutorial and a link collection on safety and security. And this is High Assurance Rust, highly recommended. And if you are interested in formal methods, there is an interest group which publishes very interesting interviews on YouTube. And the last link is my personal favorite project in Rust, which is an embedded asynchronous executor. So basically an environment which can directly run on bare metal of Cortex-M and have multitasking, especially with networking, USB stacks and everything in place. And thanks a lot. I just see the question on the chat. Let me just quickly read. Yeah. So Rust does not have exceptions, but it has this results. And this question mark is just a syntactic sugar. So basically a nice way of writing, matching the result of that function. And if it's an error, just return that error to the calling function. And if not, just proceed. Personally, I believe that this is much more safety conformant because it's not a hidden execution flow, but instead visible by using this question mark operator. And it's also, the compiler will enforce that errors are being handled. Otherwise, the return value of that function is still wrapped in a result. And so you first have to handle this result before you get access to the underlying value.
Thanks. Maybe I can take the second question,
yeah.
which says, will Rust be part of the adaptive AUTOSAR standard? If so, do you suggest that software tests for Rust have to be provided as well? So one thing that we need to clarify, in fact, we were asked to put that as a disclaimer as well, that the vendor development is still not intended to be moved to Rust. This is now our first step to just show that the adaptive applications themselves could be probably programmed in Rust. Whether we would have some kind of integration tests, or for specific projects, companies would like to have integration tests developed in Rust as adaptive applications to basically test your adaptive AUTOSAR features. That's completely then the project-specific decision.
Of course, the Rust demonstrator code comes with unit tests, which you can execute. And these check the compatibility of the stack with the Rust APIs, which are right now totally stack agnostic and should be portable across vendors.
Yeah, thanks, Christof. Right, so further questions? We still have about 2 minutes. So, Christof, I'm assuming that would be more a question for you. What tool support exists for Rust? Example in terms of coverage, etc.
Yeah, actually, I just recommend to take a look at the highassurance.rs because there are also just links there. I don't recall the tool but there is a tool for coverage as well. There is Cargo Cuff, as far as I recall, but there might be a better option as well.
Thanks. So
and
other...
of course, Rollout operating system, of course, also supports Rust already, if you count that as an automotive software platform. Which I
okay,
do.
So that would be the answer to the second question, whether there is another automotive software platform that uses Rust. Okay, good. Thanks. Yeah, we I think are just closing up on our time. If there is no further question coming in, then yeah, I would like to thank you from my side, and I
also from my
same
side.
from the Christof. Right. Thank you, and yeah, then I'll stop sharing.
Thank you so much.